Welcome back to Lawrence Tech in sunny Southfield, Michigan. And today's topic is going to be cross products, and we'll do a simple example. You've seen that wrench before, so we already know what the answer is in terms of the moment about the center of that wrench there. So we can try using this cross product method to see if we get the same results and show that how much easier that can be, even on a simple thing. Now, I will take just a second here, remind you the dot product is two vector A dot B is equal to magnitude of A, magnitude of B times the cosine of the angle between them, and the result is scalar. Okay, we did that, and we used that to project one vector onto another. Typically, we will project a force onto a unit vector pointing in the same direction as a position vector, and so we can get the proportion of the force acting along that line. So that was the dot product. Let's not let that get confused with our cross product. The definition of the cross product is similar, but different, obviously. A cross B is equal to, by definition, the magnitude of A, magnitude of B, sine of theta, and times, and this is important, a unit vector in direction C, okay? So this portion here is the scalar magnitude. Oops, I missed. And this portion here is the direction. So right away we see a big difference is that it's a vector instead of a scalar, and the direction vector is basically normal or perpendicular to the AB plane, and the direction of that vector, or the sign, is found by using our right-hand rule. So when we do a cross product, it's just like when we looked at calculating the moments for our scalar examples, the moment has a direction that's perpendicular to the plane defined by our position vector and our force vector. So in our example here to the left, the U sub C will be pointing in this direction straight up from that XY plane. Now, as you see, we're using a sine instead of a cosine, so that means that, for example, a few quick ones, I cross J is equal to K. K cross J is equal to minus I. Again, from our right-hand rule, going from K to J, we're going clockwise, and that gives us a minus sign on our vector, which is at right angles. And also, I'll point out that I cross I equals 0. Okay, so also J cross J, et cetera, et cetera. So when we do our cross product of two vectors here, if I do A cross B, didn't leave enough room, I'm going to write this out. I'm not going to actually do it. There's two different forms here, and I just want to show you AXI. So I skipped over making you sit there and watch me write this stuff. But we have two forms of A cross B, where I take each individual term in my Cartesian coordinates and cross those at one at a time. And I have this determinant form here. We can do the same math by evaluating this determinant. I'm going to leave it to you to fully work this out if you want, but remembering that I cross I is 0, so if I were to look at multiplying this out, AXI times BXI, that term goes away, right? AXI times BYJ, that gives me AB times K, and here's K, and there's the AX and the BY. So there's those terms in that determinant that you would find, and then AX times BZ, I across K gives me J, and those terms AX, BZ, and J are there in the determinant. And if you kind of follow the whole thing through, you find that by evaluating that determinant, which is fairly straightforward, we can get the same answer as multiplying everything out, and the determinant form is much more compact and easy to work with. So if we want to apply the cross product to the moment of a force, recall the moment about point 0 is a vector equal to R cross F, right? I guess that's not recall, that's how we use it. Where R is a position vector from O to any point along that force vector, or along the line of the force. Okay? And we talked about that last time, and F is the vector pointing to that force. So let's run our example here. So given our wrench example from before, we defined this position vector R is equal to, I've got 2.5 centimeters in the X direction, so I've got, in meters, that's 0.025 I, and I have minus 15 centimeters in the Y direction, so that's minus 0.15 J, and plus 0 K. This is just a two-dimensional thing, and our force is noted right there, F equals 6I plus 6J plus 0 K, and to do my cross product, I want, and it has to be R cross F, the position vector cross the force. If you get it mixed up, you're going to get the wrong answer. So my moment about 0 equals R cross F equals, and I'm going to write it in my determinant form with I, J, K in the top row. Those are my unit vectors along each axis. And in the determinant itself, I write R as the first one, so it's 0.025 minus 0.150. F is 660. And if I multiply this out, I'm going to change those lines a little bit here. There we go. So I've got a little bit of room. Yeah, I start out with I. When I multiply with I say it's the minus 0.15 times 0 minus 0 times 6. Well, those terms are 0, so I've got 0I. And if I look at the multiplying out the J term, it's 0.025 times 0 minus 0 times 6. Again, that's 0, which we'd expect. And the K term, it's 0.025 times 0, that's 0, or excuse me, not times 0, 0.025 times 6 minus 0.15 times 6. And I should really use the stars, not dots, so we don't get that confused, times K. And if I multiply those out, I get 1.05 K Newton meters, because the position was in meters and the force was in newtons, okay? And that's the same answer we got last time. That's our example. It's pretty straightforward. Once you have these vectors in the Cartesian notation, you've got your position vector and this, because it's a moment, it's a full position vector, not just a unit vector, and you've got the force in Cartesian coordinates. You can write it in this determinant form and just turn the crank, and that's it. So that's my quick example. I'll do another example with the actual 3D case where we can work it out in the next video. But until then, have a good time. Bye.